Okay guys, we're in chapter 7 and we're looking at problem solving, and today we're going to just do some sample problems. I can't do an example of everything for you, but I'm giving you some examples of different things that you could see. Okay, we're going to look today starting at chapter 7, problem 12 at the end. It says a steel cable is laying flat on the floor, drags a 20-kilogram block across a horizontal frictionless floor. A 100 Newton force applied to the cable causes the block to reach a speed of 4 meters per second in a distance of 2 meters. What is the mass of the cable? Now notice they're asking us the mass of the cable. So if they're asking us the mass of the cable, then we cannot assume that we have a massless cable. So the cable has to be treated like an object in our system. So let's start looking at problem solving here. Now you've got a copy of this in the handout I gave you on how to do things, okay? But I'm going to write it out because that slows me down a little. Now, we have a block and we have a cable. Okay? Now, the block is 20 kilograms. It's going to have a normal force on it, a force due to gravity, and it's going to have a tension T1. Okay? Now, the other things it tells us is that this guy is frictionless. Okay? So I really don't have to worry about doing the sum of the forces in the y direction because I don't need the normal force because I'm not going to be calculating a frictional force. All right? So the acceleration I'm going to make in this direction, A1. I can say the sum of forces in the x direction equals T1, which equals mass of the block times A1. Okay? Now, the only thing I have right now is the mass of the block. So T1 is equal to 20 kilograms. And it tells us the acceleration. It's the block reaches 4 meters per second in a distance of 2 meters. So V initial was 0. V final was 4 meters per second, and in 2 meters. So I can use V final squared equals V initial squared plus 2ax delta x here, and I can go 4 meters per second squared has to equal 0 squared plus 2 times ax times 2 meters. Okay? So 4 squared is 16 divided by 4 says that ax is 4.00 meters per second squared. Okay? So now that I have AX, I'm going to scoot this over just a little bit. I can come back up to this equation, okay, and say that T1 is equal to 20 kilograms times 4 meters per second squared. So that's 80 newtons. Now let's look at our cable. MC, we don't know. Okay, but if I look at the cable, there's going to be a T2 and a T3. Of course, there's a normal force and a force due to gravity. I'm not going to worry about those because it's a frictionless table. Okay? Now, the sum of forces in the x direction is going to be T2 plus T3, and that has to equal the mass of the cable times the acceleration of the cable. Okay? Now, T2 has to equal T1. They're at the same end of the cable. This is an action-reaction pair. So I know that this is 80 newtons. Okay? I know that AC has to equal A1, which was a 4.00 meters per second squared. That's the acceleration constraint. And we're told in the problem that there is a 100 Newton of force being applied to the cable. So T3 is 100 newtons. That was a given. So if I plug those in, I have 80 newtons negative plus 100 newtons positive has to equal mass of the cable times 4 meters per second squared. So 100 minus 80 is 20 divided by 4 says that the mass of the cable is 5.00 kilograms. And you know, it's a quarter of the mass of the box. It's definitely not negligible. Okay? All right, so follow along in the problem on the paper that I gave you. Now let's move on to our next problem. Let's see, we've already done 14. We're going to move on to problem 24. Okay. It says one block is tied to the wall with a rope. It sits on top of a 2 kilogram block. The lower block is pulled to the right with a tension of 20 newtons. The coefficient of kinetic friction at both the upper and lower surfaces of the 2 kilogram block is 0.40. What is the tension of the rope attached to the wall, and what is the acceleration of the 2 kilogram block? All right, guys. You might want to start just with a rough sketch of this before you do the free body diagram so that you understand how things are moving and what directions frictions are going to apply. So I'm going to start with that, okay? And we'll go from there. Now, if I do a rough sketch here, there's the wall, there's a rope, there's the top block, there's the bottom block. Okay, and it's being pulled that way, and that's the floor. Now, acceleration of the bottom block is going to be this direction. That means that the frictional force, I'll call this F1 here, is going to be in that direction. That's F2 in that direction. The top block is going to experience a frictional force F3 in the other direction. And it has a tension force T1 in that direction. Okay? And we have a force here of 20 newtons. Okay, so that's our rough sketch. The reason I wanted to start off with a rough sketch is so that you could kind of get in your mind what directions all the frictional forces were going to point. Okay? So this was always a good place to start. On a test, I will be giving you the initial drawing, sketch on it. Okay, it's always a good idea. Now, this bottom block is 2 kilograms, and the top block is 1 kilogram. I'm going to need 2 free body diagrams, one for the top block, one for the bottom block. Okay? Now, I'll look at the top block then. There's normal force, I'll call it N1. Force due to gravity, 1. There is the tension, T1. And there is a frictional force, F1. Okay? I know that the mass is 1 kilogram. So the force due to gravity is going to have a magnitude of 9.80 newtons. Okay? Now, the sum of the forces in the x direction on this guy are going to be 0. Sum of the forces in the y direction on this are going to be 0. So if we look at the sum of the forces in the y direction, I'm going to get the normal force plus force due to gravity 1, adding up to be 0. So the normal force, I don't know, but the force due to gravity is 9.80 newtons. So the normal force has to be, well, that's minus 9.80 newtons. So I can get F sub k as being mu sub k, and in this problem the mu is 0.40 times 9.80 newtons. Okay guys, we're back. Sorry I had to take a little break. Somebody was at the door and had a question for me. So the other thing I want to draw on here is my acceleration. The bottom block should accelerate in this direction. Now, before I can calculate the frictional force on the bottom, I have to get the normal force from the floor. So I'm going to look at the sum of the forces in the y direction. It's going to be the normal force from the floor, force due to gravity in the bottom box, the normal force from the top, and that all should sum up to be 0. So the normal force of the floor plus, and I see this was a 2 kilogram box. So the force due to gravity on this is 19.6 newtons. So minus 19.6 newtons plus a minus 9.80 newtons has to be 0. So the normal force with the floor, 19.6 plus 9.8, 29.4 newtons. So the frictional force with the floor is going to be 0.40 times 29.4 newtons. So 0.4 times 29.4, 11.8 newtons. Okay? Now, I have this force, I have the 2 frictional forces, I've got all the forces in my x direction. So the sum of the forces in the x direction would be the frictional force from the top plus the frictional force from the floor plus the plus 20 newtons, and that has to equal the mass for this bottom block times the acceleration. Let me make sure you can see all that. Okay. So, the frictional force from the top is going to be a minus 3.92 newtons because it points in the negative direction. The frictional force from the floor is minus 11.8 newtons. Then we've got our 20 newton force has to equal 2 kilograms times A. So let's sum it all up. 3.92 negative minus 11.8 plus 20. I get 4.28 newtons equals 2 kilograms times A. So divide through by 2. So I get 2.14 meters per second squared is equal to A. And it's positive, which is the direction we had it drawn. Okay? Now, guys, this is all about writing out as much information as possible first. Okay? Looking for action-reaction pairs. And seeing if there are any acceleration constraints. Okay? Now, let's move on. The next problem we're going to look at is problem 41. I like 41 because it gives us an opportunity to play with angles. Okay? Now, as we look at problem 41, you've got a cup, okay? You've got a 1 kilogram physics book that is connected by a string to a 5-gram coffee cup. The book is given a push up the slope and released with a speed of 3 meters per second. The coefficient of friction, static, is 0.5 and kinetic is 0.2. How far does the book slide? Okay, so we're going to attack part A first. How far does the book slide? Now, again, you may want to do a rough sketch of that and draw, think about all your forces, kind of sketch them in before you do a free body diagram. You may just want to jump into the free body diagram. Take as many steps as you need to be successful. Okay? I'm going to jump straight into my free body diagram. Now, we've got the cup, and the mass of the cup is 0.500 kilograms. I'm going to go ahead and calculate the force due to gravity. So it's going to be 9.80 meters per second squared times 0.500 kilograms. So that makes it 4.90 newtons. Okay? Now, if I do a free body diagram of the cup, there's going to be a tension T1 in the rope, and I'll force due to gravity on the cup. Okay? And this guy, since it's going to be slowing down, our acceleration vector needs to point in the opposite direction of velocity initially. So velocity initially was up, acceleration vector should be down. Okay? So, the sum of the forces in the y direction has to be T1 plus force due to gravity of the cup, and that has to equal the mass of the cup times A1. Okay? So I've got T1 minus 4.90 newtons is equal to 0.500 kilograms A1. Right now I've got one equation and two unknowns, but that's all I can do with the cup. Now let's go to the book. Now the book is on an inclined plane, and this angle is 20 degrees. Okay? I'm going to make my plus x-axis up the inclined plane. My plus y-axis then is perpendicular. We've got a force due to gravity on the book. Okay? The mass of the book is given to us as 1 kilogram. So the magnitude force due to gravity of the book is 9.80 newtons. Now, if that's a 20-degree angle, this is a 70-degree angle. Okay, force due to gravity of the book is force due to gravity book y component force due to gravity book X component. Now, if I was doing this for myself in fact, I'm going to do it for you guys too. I have a tendency to work with colored pens or colored pencils, and I would probably do this force due to gravity Y direction for the book, force due to gravity X direction for the book, force due to gravity on the book. So I know that those are component vectors. Okay? And then there's going to be a normal force. And there's going to be a frictional force. Okay? The frictional force is going to point down the inclined plane, frictional force, and there is a tension. I'll call it T2. Now, the acceleration vector, A2, is going to point down because velocity initially was up. All right, now, I know that the magnitude of T2 has to equal the magnitude of T1, and I'm just going to call that T. That's going to come in handy in a minute. I know that magnitude of acceleration A1 has to equal the magnitude of acceleration A2, that's A, because they're connected directly by the string. That's our acceleration constraint. Okay? Now, I'm going to take my force due to gravity and I'm going to divide it up into X and Y components. So I'm going to take the force due to gravity, 9.80 newtons, and multiply times the cosine of 70 degrees to get the X, 9.80 newtons times the sine of 70 degrees to get Y. So 9.8 times 70 cosine, that's 3.35 newtons. 9.8 times 70 sine is 9.21 newtons. Okay? Now, I'm going to go after the sum of the forces in the Y direction first. Two reasons. Number one, in the Y direction, the sum of the forces is 0. And number two, I need the normal force to be able to calculate the frictional force. So the sum of the forces in the Y direction, that's going to be the normal force, plus force due to gravity in the Y direction on the book, and that has to add up to be 0. And mu sub k is 3.92 newtons. So if I look at the sum of the forces in the X direction, I have T1 plus F sub k, 1, is going to be 0. So T1 plus 3.92 newtons equals 0. So T1 is 3.92 newtons. Okay, so we've got the tension in the top block. Now, if we look at the bottom block, okay, there's a frictional force with the floor, a frictional force top. There is that 20 Newton force that's being applied to it. Okay? Now, there's a force due to gravity. I'll put B for bottom. There's a normal force from the floor, and there's also a normal force from the top block. Okay? the frictional force on the top is equal to the frictional force 1 from the top block, which was 3.92 newtons. Okay? The normal force top has to equal the normal force 1 on the top block, which was 9.80 newtons. Those are action-reaction pairs of forces. Okay, now let's think about that for just a second. I've got to take care of something. Be back in a second. So I get the normal force plus minus 9.21 newtons equals 0. So the normal force is 9.21 newtons. Okay, that means our frictional force is equal to our mu sub k, 0.20 times 9.21 newtons. So 0.2 times 9.21, this gives me 1.84 newtons. Okay, let's roll this just a little bit. Now, we look at our sum of the forces in the x direction. I have T2 plus force of gravity in the x direction on the book plus the frictional force, all having to add up to the mass of the book times the acceleration of the book. Now, T2 is equal in magnitude to T1, which is equal to T, and it's pointing in the negative direction, so I have minus T. Force due to gravity on the book in the x direction is going to be a minus 3.35 newtons because it's in the negative, and the frictional force is a minus 1.84 newtons because it's pointing in the negative direction, and that has to equal 1 kilogram times a minus a, because I said the acceleration is in the negative direction, it has a magnitude of a. Now I'm going to take my other equation here. I said that T1 equals T2 equals T, so I get T minus 4.90 newtons is equal to 0.500 kilograms. And I said that A1 equals A2 and it has a magnitude of A, so this would be minus A. So now I have two equations, okay? I'm going to solve this one for T. So T is going to equal 4.90 newtons minus 0.500 kilograms A. I'm going to sub in here. So I have the negative of 4.90 newtons minus 0.500 kilograms A minus, let's see, 3.35 plus 1.84, 5.15 newtons equals a minus 1 kilogram A. Okay, guys. So if I take the negative sign in, I have minus 4.90 newtons plus 0.500 kilograms A minus 5.15 newtons equals a minus 1 kilogram A. So I take that over, have a minus 1.50 kilograms A is equal to, let's see, 3.35, that should be 1.9. I thought I made a mistake there. Sorry guys, this is minus 5.19. I transposed wrong. So negative 5.19 minus 4.90 have a minus 10.09 newtons I divide through by 1.50, and I get a minus 6.73 meters per second squared. Well, excuse me, the negatives divide out. It's positive. I expect to get a positive there because A, as I'm solving for it, here is a magnitude. Okay? So if I want A1 and A2, they're both negative. So A1 is a minus 6.73 meters per second squared. A2 is a minus 6.73 meters per second squared. You make sure I got the same thing both times. No, I got something different. Let's see. 1.84. Let's see, FGX. I always just double check, guys, to make sure that I have put everything in correctly. FGX, tension, normal force. Okay. Yep, everything looks good. Okay. Now, we've got part A done. But now it asks me about part B. It says, when it gets to its highest point, does the book stick? Okay? Now, what we need to ask ourselves is, what kind of frictional force do I need to hold the book in equilibrium? So, I am going to be working with a slightly different equation this time. Okay, so let me erase some stuff here, so we got some room to work. Okay, now the sum of the forces in the y direction on the cup are going to add up to be 0. So T1 plus force due to gravity on the cup should add up to be 0. So T1 should equal a plus 4.90 newtons. That means that T2 is going to be 4.90 newtons. Okay? And this time, the frictional force is going to be up the inclined plane because the book is going to want to try to slide down. Now, the magnitude of the frictional force, we'll worry about in a minute. We're going to solve for it and then compare it to F sub S max. So, the sum of the forces in the x direction here would be T2 plus force due to gravity x plus our frictional force. And if it stays still, the sum of the forces in the x direction have to equal 0. So T2 is going to be a minus 4.90 newtons. Force due to gravity in the x direction, let's see, it's 1 times, let's see, so it was 9.8 times just 3.35 newtons, and that's negative, plus the frictional force has to equal 0. So the frictional force needed to keep it sitting still is 8.25 newtons. Now, F sub S max is going to be equal to mu sub s times the normal force. Mu sub s was 0.50, and the normal force on this was 9.21 from part one of the problem. I don't have to reinvent the wheel. So 9.21 times 0.50 is 4.61 newtons. Now that's the maximum frictional force needed to keep it in place. That's the actual frictional force I can apply maximum. Okay? If I look at this, the F sub s max is less than 8.25 newtons. So the book slides down. Okay, so now I know the book slides down. Okay? And that's all it asks us. The last thing it asks us, will the book slide down? And the answer is yes. Okay guys, that's the end of question 41. I only want to work one more problem for you, and that's problem 55. Now, it's not uncommon for us to run into systems of equations. Okay, so expect them. Now, let's look at problem 51. No, excuse me, problem 55. Now, the reason I want us to look at problem 55 is because of the way the rope moves. Okay? It says, what is the acceleration of the 3 kilogram block shown in figure 7.55 across a frictionless table? Now, rope's tied here, it loops around the pulley, it loops around this pulley and attaches to a 1 kilogram block. Now, I want you to think about the fact that essentially both sides of this rope, the rope on this side of the pulley and this side of the pulley, are both pulling on that 3 kilogram block. The other thing I want you to realize is in block 1 moves a foot, the 3 kilogram block is only going to move half a foot because of the way the rope is looped. So the acceleration constraint is going to be a little different here. Okay? So I want you to think about that for me. How is that going to affect our acceleration constraint? Okay, guys. Now, we've got our 3 kilogram block, and we've got our 1 kilogram block. Okay? Our 3 kilogram block has a normal force, a force due to gravity, and then it's got a T1 and a T2. And it should be accelerating A1 in this direction. Okay? Now, there is no friction. So I'm not going to worry about the sum of the forces in the Y direction. But if I look at the sum of the forces in the X direction, I have T1 plus T2 has to equal the mass, which is 3 kilograms, A1. Okay? Now, for the hanging block, there's going to be a T3, force due to gravity on the block. Now, the force due to gravity here on the block is 9.80 newtons, because 9.8 times 1 is 9.80 newtons. Okay? And the acceleration here is an A2, and it's going to be down. Now, I know T1 plus T2, well, T1 has to equal in magnitude T2, which has to equal in magnitude T3, because it's all the same rope. Okay? The other thing I know is that A2 in magnitude is going to be 2 times A1, so I'm going to call it 2A. Okay? That's our acceleration constraint. There's our action-reaction pair, or you could say it's our massless string assumption. So if I look at the sum of the forces here in the y direction, I have T3 plus force due to gravity B is going to equal A2 times the mass, 1 kilogram, A2. Now let's start subbing things in. So I have, if I look here, I have T plus T is equal to 3 kilograms times A. Here, I have T minus 9.80 newtons equals 1 kilogram times a minus 2A. Okay, so I have 2T is equal to 3 kilograms A. So I could say T is 1.50 kilograms A. Substitute that over. 1.50 kilograms times A minus 9.80 newtons equals a minus 2 kilograms A. So minus 9.80 newtons equals a minus 3.50 kilograms times A. The negative and negative cancel out. So A is going to be 9.8 divided by 3.50. So I get A to be 2.80 meters per second squared. So vector A1 is a plus 2.80 meters per second squared. Acceleration vector A2 is going to be a minus 5.60 meters per second squared. Okay? So, everything works on this general idea. First thing you always want to do here in this chapter when you're problem solving is, you may want to start with a rough sketch of what you've got going on a test. The picture will be there, sketch on it. And then move on to, free body diagrams. Always calculate your force due to gravity first. If you've got frictional forces, then move on to calculate your normal force. Look for action-reaction pairs. Look to apply the massless string assumption. Apply your acceleration constraint. Work on building equations. And then look at solving systems of equations. And once you've solved for something, you can solve for everything else. And it's just a back and forth process. Okay, if you start at one thing and it doesn't seem to be working, move on to the other object. I usually start with the object that has less forces acting on it, but notice in this example, I started with the other one. But because it was frictionless, a couple of those forces weren't going to be important to the problem. Okay, guys, that's the end of chapter 7.